Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3. Open Methods. Fixed Point Iteration Method. The fixed point iteration method is a numerical technique used to find the solution to equations of the x equals gx form, where x equals gx is a function derived from the original equation. This is often the most difficult part of the process and requires a function gx that leads to convergence. The idea behind the method is that if we can rewrite the equation as x equals gx, referred to as the fixed point, we can then iteratively update guesses for the value of x until they converge to the solution. Consider the curve y equals gx and the line through the origin, y equals x. We start with the fixed point iteration method by selecting an initial guess sufficiently close to the root. We will denote it with x0. We then find the point of vertical projection on the curve, which we will denote by y0. Using this point, we project it horizontally on y equals x to find an improved estimate x1. For the current estimate, we find the point of vertical projection on the curve, that is, y1. y1 is then projected horizontally on y equals x to find the new and improved estimate x2. We repeat the projections until the points on the curve converge to a fixed point. Every vertical projection to the curve by yp equals gxp is followed by a horizontal projection to y equals x. For a given nonlinear equation, several alternative forms of the iteration function can be obtained. For example, 4x squared plus x equals e to the minus x. We obtain 4 iteration equations. Which one is better to use? Assessing the convergence behavior of an iteration equation, we assume gx and g'x are continuous functions in an interval, a, b, in which a root lies. A sufficient, but not necessary, condition is that the absolute value of g'x is less than or equal to lambda less than 1 for all x on a, b, where lambda is an upper bound. The initial guess should be close enough to the true root. After a sufficient number of iterations, lambda gives the convergence rate. That is, the following figures depict two converging cases. Fixed point iteration method convergence is assured if the absolute value of g'xp is less than 1. The following figures depict two diverging cases. The fixed point iteration for illustrated cases diverges because the absolute value of g'xp is greater than 1. The advantages of the fixed point iteration method are: the method is simple and easy to apply. Its cost per iteration is low. If it does converge, it may converge very slowly. Its convergence rate can be estimated simultaneously with the root. The disadvantages of the fixed point iteration method are: the method requires an initial guess that is sufficiently close to the root. Even then, the convergence may not always be guaranteed. The convergence property depends on the choice of iteration function g, x, i.e., finding a suitable iteration function can be a major problem. Several stopping criteria can be applied either in terms of absolute or relative error. In the relative error criterion, a small number, the delta, may be added to the denominator, preferably in the order of machine epsilon, to ensure convergence in the case of 0 or very small roots. It is recommended to use two criteria to ensure correct estimation in the case of very small or very large roots. Consider the following nonlinear equation. Find its root, if it exists, in the interval from 1 to 2. For the initial guess and convergence tolerance, use x0 is equal to 1 and an absolute error less than 5 times 10 to the minus 5. This nonlinear equation can be expressed in two different fixed-point iteration forms. In the first one, we isolate x. The right-hand side becomes gx. Its derivative is 5 times x to the fourth. This derivative in the interval from 1 to 2 ranges from 5 to 80. Therefore, this equation form will diverge no matter how close the initial guess is to the root. The second form is obtained by first isolating x to the fifth. The right-hand side becomes gx. Its derivative is found as follows. We note that g'(x) for x values from 1 to 2 ranges is less than 1. Therefore, this form of gx will converge with any initial guess in this interval. We start with the initial guess of x0 equals 1. The vertical projection on the curve is found as follows. The value of 1.362761 is projected on the origin line. This is recorded as x1, that is, it is the first step estimate. Next, we calculate the absolute error between x1 and x0 estimates. We repeat the same procedure starting with x1. The vertical projection on the curve is found as follows. The value of 1.383176 is projected on the origin line and it is registered as x2. The absolute error between x2 and x1 is not small enough yet to terminate the process. We repeat the iteration starting with x2. The vertical projection on the curve is found as 1.384290, which is projected on the origin line and it is recorded as x3. The absolute error between x3 and x2 is 0.0011137. We continue the iteration process in this manner. We obtain the converged result after 4 iterations. The fifth estimate is 1.384354, which has satisfied the stopping criterion. Comparing the solution with the true root, we find that the final estimate has yielded the true error of 1.3 times 10 to the minus 8. That is all for now. See you next time with another topic. Bye.